In this video, we'll be discussing the mean, variance, and standard deviation of the discrete probability distributions we discussed in the first video from Chapter 5. Recall that in Chapter 3, we examined how do we calculate the mean, variance, and standard deviation using raw data. So that is using the 1, zeros, using the different numbers or whatever that we have from individuals. Now we're going to discuss the same concept, but when we have been given the probability distribution, that is each of those individual values of x and their probabilities. Previously, we calculated the mean by adding across all the values and then dividing by the total number of observations. Now what we're going to do instead is to take each of the values, that's those x values in that top of the column, and multiply by each of the probabilities in the bottom. So looking at our graphic, we have the probability of x, we have x. So we're going to take each one of these x values and multiply by each one of their probabilities for each one of these things going across. That's our goal. In equation form, we can write the sum of each of the x's, that's x sub I, times the probability of p of x sub I. So in this case, we have the first x times the probability of the first x plus the second x times the probability of the second x, excuse me, and so on, as is seen above. Note that the x's are those outcomes, again, that top of that sideways table. The probabilities are the corresponding probabilities. All right, so for our first example, let's do this with rolling a die. We've got the outcome, 1, 2, 3, 4, 5, 6. We've got each of the probabilities, 1/6 for each one. Now we're going to calculate the mean of this discrete probability distribution. So our equation in the equation form is all of the x's times all of their probabilities, and then summing all of those values up. So thinking this through, kind of what we described earlier, we're going to take this first x value times the probability plus the second x value times the probability plus the third x value times the third probability, etc. Writing this out, we get 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, and so on. Sticking this into our calculator, we find the answer is 3.5. So the mean of this discrete probability distribution is 3.5. Please be careful and note none of the actual x values are 3.5. That is, you can't roll a 3.5 on a die. What the mean is if we rolled a die over and over and over and over and over and over again, and then took all of those values and divided by how many we added up. So let's say we rolled a die 100 times, added up all those values. The first time we get a 4, second time we get a 1, third time we get a 6, etc. Added all those up, and then divided by the 100 times we rolled the die. That would tend to be next to this 3.5 number. And if we did it 1,000,000 times or 1,000,000,000 or 1,000,000,000,000, that's going to be exactly 3.5. Can do this with tossing coins. So the number of heads, 0, 1, 2, and 3. If we toss 3 coins, and then 1/8, 3/8, 3/8, 1/8. Try this on your own. See how you do given this. Go on and pause the video. So checking your work. Make sure you multiplied each of these times their individual probabilities. So make sure that you started at 0, whatever the x value is. It doesn't always go in numerical order. It doesn't always go 0, 1, 2, 3 or 1, 2, 3, 4. Sometimes you skip a few, etc. Probabilities aren't always the same, so make sure the 3/8 are paired with the 1 and the 2, and the 1/8 with the 0 and the 3. And remember, 0 times 1/8 is just 0. Adding all these up or plugging them into a calculator, you should get 1.5. Again, this doesn't mean you can flip 1.5 heads and 3 coin tosses. It means that if you did 3 coin tosses, counted the number of heads, did 3 coin tosses, counted the number of heads, and did that over and over and over again, that experiment, then took the average number of heads, the mean is that average. For one more example, probability distribution of vacations exceeding 5 days, this is the number of trips we're looking at. Of course, this is probably decreased. So give this one a shot on your own. Take a minute to pause the video. Then we have, checking our work, 0 the number of trips x times the probability, 1 the number of trips x times the probability, etc. So people are 70% likely to take 1 trip greater than 5 days, 20% likely to take 2 trips greater than 5 days, 3% likely to take 3 trips greater than 5 days. Overall, on average, for the average American adult, on average, they take 1.23 trips greater than 5 days. And again, please remember that when you're looking at these kinds of averages, even when you're looking at averages of raw data, that average does not mean that any individual actually took 1.23 trips. It's like saying the average number of children in a household is 2.5 or 1.5. No family has 1.5 kids. No family takes 1.23 trips. All right, so just like we calculated the mean a little bit differently, the variance and standard deviation are going to be a little bit differently too. There's 2 ways to do this. This one is computationally easier. It's 1 step shorter. I tend to prefer this one though because it follows that same table we had. Remember the table that we had previously when we were calculating our standard deviation? We had x, then we had x minus the mean, then we had x minus the mean squared. So now if we're doing this, we're going to have the probability of x and then x minus the mean squared times the probability of x. This is going to be the end of our table here. So because this second way uses that table, I tend to prefer that second way a little bit more personally. Standard deviation is going to be the exact same calculation. The square root of whichever of these formulas you use up here. I have the first one there, but it can just as easily be the square root of the sum of the quantity x minus mu quantity squared times the probability of x. So on this, why don't you on your own go on and try out this equation. Try calculating the probability of, or excuse me, the variance for rolling a die. Do the variance and standard deviation. All right, coming back. This is the first calculation, just what I have built in my slides here. So I'm going to square each of the values, multiply by the probability, then subtract the mean. I get around 2.9167. This should match with what you get, whether you did it this way or the other way. Again, that I tend to recommend when doing it by hand. And again, your standard deviation is just going to be the square root of that number, 1.7078. Now think about if we're filling out this table with our different values. We're going to start with the different values x. These are going to be the different x values that are listed. Then we have minus the mean. So remember the mean in this case is 3.5. So we're going to subtract the mean from each one. Minus 2.5, minus 1.5, minus 0.5, positive 0.5, 1.5, and 2.5. Then we're going to square each of these values. We can put in the probabilities for each one of these. Each one of these has a probability of 1 over 6. And that's enough 1 over 6's. And then we would multiply whatever the squared value was times the probability to get our number in this section. And then we're going to add up, remember this sideways e, this sum. We're going to add up all of these numbers for all of these 6 sections. And this is going to give us our variance. Try that for the vacations data too. Go on and give it a shot, calculating the variance and standard deviation. Again, in my slides, I'm doing it the quick way. It just lets me keep everything on a single slide. So in this way, I'm squaring each of the x values and multiplying by the probabilities, and then at the very end subtracting the mean squared. If you're doing it the other way, that's just fine. So double check your work and make sure you got the 0.4171. If you didn't, maybe go back. If you're just a couple places off, so 0.4, I don't know, 172 or something like that, might just be rounding error as you're multiplying these on your calculator. After you have that value, make sure you can get the standard deviation by taking the square root of that value. Standard deviation is about 0.6458 trips. Closing this out, we'll talk about statistical expectation. Statistical expectation is just a fancy word for saying the mean of a distribution. It's the theoretical average of the random variable that we're looking at. Note that this is different than a real mean where we actually can observe the different values. In this case, this is theoretical. In other words, what we would expect to happen. Now, this theoretical average is actually the exact same average formula as we have. So if we have our discrete probability distribution, then the expected value of the random variable that we have the discrete probability distribution for is just the mean of that discrete probability distribution, what we were just working through. We use this e of x, and that's how this is enunciated, e of x, or the expected value of x, to indicate the expected value. Now, this is often done in cases like gambling or betting. So if we're looking at winning tickets, we have a whole bunch of tickets that are being sold at $1 each for something that's valued at $350. What's the expected value of gain if you bought just one ticket? So first, actually one of the hardest parts in the expected value is creating a table. So I'm going to switch. You can jot this down on your own if you want. I'm going to switch to my writing utensil here. One of the hardest things that we have is creating the table for this, that is identifying what are my x values and what are the probabilities of x. Now recall in this example, I'll flick back real quick, that we're selling 1,000 tickets at $1 each for a color television. So you have to pay $1, but if you win a television set that's valued at $350. So one way that's kind of nice to look at all of the different options in the expectation is to think about what if I win and what if I lose, and look at those two options as the two x values we're going to examine. Now if you lose $1, that is minus $1 is your x value. If you win, you won $350, but you actually paid $1 for the ticket, so you're only going to walk away with $349. And if you think that you actually won a whole $350, then at any time I will give you $1 and you can give me $10 back, and you can walk away having won $1. It'll be great. We can do that, play that game as many times as you want. So in this case, again, think through why this is $349. This guy right here, why is that $349 as opposed to $350? And it's because you still had to pay $1 for the ticket. Still had to pay $1 for the ticket. Now for the probabilities. What's the probability of winning versus losing? Well, you buy one ticket, and there are 1,000 tickets sold. So there's only one winning ticket. There's 1,000 possibilities. The total sample size is 1,000. The number of events for winning is just 1, so we get that 1 divided by 1,000 from our classic probability. For the probability of losing, think about if there's one way to win, how many ways are there to lose? There's still 1,000 total tickets, 1,000 options, and if there's one way to win, well, there's 999 ways to lose. So in this case, to find the probability of my x, again, this is the hard work. We were already doing the probability of x, the probability of x is just taking each of these values, 349 times 1 over 1,000 plus -1 times 999 over 1,000 to get our response. One big thing that I'll highlight, maybe I can circle it in red here, is do not forget the negative part of this, the -1. The -1. That's a very important piece that some students forget. You could also just subtract 1 here, so you could do -1 times 999, whatever works best for you, but don't forget that this is losing money, that this right side is losing money here in comparison to the left side where you're actually gaining money. So don't forget that. Going back to our slides, we see, hey, the tables match up to what we did by hand. And calculating this out, it looks like we lose about 65 cents per play. Please remember, just like before, on any single play, you aren't going to lose 65 cents. This is to say that if you played this game 1,000,000 times and then took the amount of money that you had and divided by the 1,000,000 times you played, you would lose 65 cents per play on average. This is on average. This isn't for any individual game that you play. For an individual game that you play, you can win $349 or lose $1. Another way that we can look at this is by comparing two different options. So in this case, two lottery games. In the first one, you pay $1 for the ticket. You've got a 1 in 600 chance of winning $500. Okay, that's not bad. In another, you pay $5, so that's a more expensive ticket, but there's a better chance of winning, right? This one, it's 1 in 600. Here, it's 1 in 400. And you would win $1,000. So go on your own and put together your two expected values tables for these two games. All right, for the first expected value table, I'm looking at X values. I'm going to win either $500 or lose $1. And then the probability of winning is that 1 in 600 chance, and then the probability of losing is everything else. If you haven't gotten a chance to, go on and put together your second expected value table. I'm going to call mine Y just to keep the X and Y straight. So X is going to be the random variable for the amount won in game 1. Y is going to be the random variable for the amount won in game 2. So looking at Y, we see that I win $995. And again, think about it's however much I quote unquote win minus what I had to pay. So 1,000 minus $5 gives me $995. I would lose $5 if I lost the game. There's a 1 in 400 chance that I win. There's a 399 out of 400 chance that I lose. Now the question isn't to put together these tables. These tables are going to be helpful to figure out how much money on average do I make in each game. The question is, if I wanted to make money or lose the least amount of money, which game would I play? So I'm going to look at the average of both of these and then compare them. So looking at the average of this first one, nope, and I see I have a typo here. It says $349. That's not true. It's $499. And it's because we had to pay that $1. So when I type out the expected value of the first game, I'm getting about, give or take, 17 cents. So I'm going to lose about 17 cents on average every time I play that game. Not every time, but if I played it a whole bunch of times, this is how much I would lose per game. Now for the second one, it looks like I'm losing $2.50 per game. That's way worse. If I could lose 17 cents per game or $2.50 per game, neither of them is great, but if I'd like to lose as little money as possible, I would want to play the first game. Note, don't forget to answer the question in these types of multi-step questions. So for the question, remember, which game would you play is the actual question you're being asked. We put together a table of expected values for both games to determine how much we would expect to make or lose, and then we used a comparison between these two numbers to determine that if we'd like to lose as little money as possible, we play the first game, or the first lottery. This has discussed how do we calculate mean, variance, standard deviation, and what is the expectation of a discrete probability distribution. Next, we'll jump into the binomial distribution, which has some similar but different rules for approaching these types of problems.